Okay, welcome to Worksheet Problem Set B. Now this is, I would say, the intermediate version from what we had already reviewed, which was Problem Set B from the book, which are practice problems. This problem set is from the worksheet itself. This comes out of Chapter 4. And I'll go into a little bit of detail with question 1, 2, and 4. I strongly encourage you to try the questions before you go further. I'll show you the question, and then I'll just have a slide where I've handwritten out the answer, and I'll go over it quickly. Here we go. Okay, question number 1 is about Joe Ponder, and he's using his teeth to lift a pumpkin. And it gives you a variety of information. You can certainly pause and look at the question itself. The question here is asking about the force exerted on his feet. And remember that his feet have to support not only the pumpkin that he is lifting, but also Joe Ponder himself. And so we have to take that into account as far as the fact his feet together are doing double duty there. Of course, his feet do not know the difference between the pumpkin or Ponder or both. Okay, the question here is then the question of course is the force exerted on his feet, but then it asks you to draw a free body diagram, or what I would call a force diagram, on what is going on with Joe. So if you have already worked this out and you want to see the reveal, it's on the next slide. So pause it now or just let it keep rolling as far as this is a video. Here is the solution, and I have set this particular question up by grasp. I went ahead and did a system schema, so I included both Joe and the pumpkin as the entire system. The ground is acting on Joe, holding him up with the support force, and the earth, of course, is pulling him down. Here is my force diagram. Basically, normal force up, force of gravity down, both on Joe and on the pumpkin. I went ahead and listed the information. I have the mass of the pumpkin, I have the mass of Joe, and the mass total is just adding those two values together. So I'm dealing with 350 kilograms, which his feet have to support. And I have gravity. There's the gravitational field strength constant. The requested or required is what is the force on his feet. The equation that I want to use is the force exerted is going to equal gravitational pull on the mass itself. It's under the solution, or the solving part of grasp, it's ready for a plug and chug. So there's my negative 9.81. Here's my mass. Multiply those two values together and I get a force, and I've rounded it hopefully to the correct number of significant figures, which hopefully this is 75.0 in the original question. I normally have done a lot better than this one to when I write down my list of variables, to actually include significant figures within the list itself. And I do have the 0 lined over so to indicate that's significant. So maybe that's where that's at. So I wouldn't need a 0.0 there because of the addition that gives me those 3 sig figs. In any case, here's my paraphrase. Joe's feet will experience 3,430 newtons of force exerted downwards as he lifts the large pumpkin upwards. Okay, that's the question and the answer. Number 2. Number 2. 1994, Vladimir Kurlovich from Belarus set the world's record as a weightlifter, the strongest weightlifter. He did this by lifting and holding above his head a barbell whose mass was 253 kilograms. And if you want to do the math, that's 2.2 pounds per kilogram. So that's over 500 pounds without doing the math. And, of course, he has his own mass of 133 kilograms, which, think about that, 2.2 pounds per kilogram there, and he's a 250-pound guy, not a small guy, of course. And then it's, in this particular case, after drawing a free body diagram, the question is asking about the force exerted on each of his feet. And so find the feet, divide by 2, that's each foot when he was holding the barbell. Well, if you've already solved, then you can go ahead and let this video continue. If you haven't solved it yet, you may want to go back and solve it and then check the solution out after this. So here we go. Okay, so here's the solution. You see the whole thing in total. Set it up by grasp again. Here is all of my information. Mass of the barbell, mass of Krilovich. So add those two together and I get a total mass. Here I have gravity, but my question is the force on each foot, not the force on the feet together. So in my analysis phase, I have the force of the feet equals gravity times mass. I realize that the foot of one, or the force of the foot of one plus the force of the other foot is going to equal the force of the feet. And I know these two forces have to be equal. So I can just find the force exerted on both of his feet and divided by 2 because it is equal. So it's really not that big of a stretch in this particular case. Under the solve portion, of course, it's just a plug and chug at this point because I did my work in the analysis phase. So here's the feet together, gravity, mass, multiplying, and that's the entire force of gravity pulling down. And of course, the normal force is pushing up, and so that's just the opposite of gravity. So negative of the negative gives me the positive 3,786 over that newtons. Well, that's the force on both feet. If I wanted the force of just one foot, or each foot rather, I would simply divide that number by 2, and then I get 1,890 newtons up for each foot. And then, of course, Vladimir should have experienced approximately 1,890 feet of applied force, normal force, support force in each foot during the lift. I have a system schema, even of course that's not asked for in any of the questions. Never hurts to do one. And here's where I'm able to identify my system as both Vladimir and the barbell together. This is how I know I want to actually add those two masses together. It's just one visual way I can show this. After that, here's my force diagram. Force of the left, force of the right foot. So both feet together here equal the force of gravity down, but each one of them is simply half of the total line. But these two forces together are equal to this one, and so I'm able to do my quality marks, or congruency marks. Okay, so there's number 2. So number 3 is about a woodpecker. When its beak strikes a tree and it gives you information there, you can work down through all of that. Of course, read the question, work down through it. If you've already worked through it, I do not have the solution worked out, but I do have the solution following. And so pause it, work it, or if you've already done so, here we go. So basically with this one, all you need to do is solve with Pythagorean's theorem because you had both of the values, and it turns out to be 4.59 newtons of net force. Moving on. Okay, here's number 4. So now we have a large gorilla, and we have a mass. We have a gorilla. He is hanging from 2 vines, each of which make an angle 30 degrees with the vertical. This is where a good force diagram, realizing where those vines are, realizing the angles to help you set up the trig, because of course trig will be employed here. Doing a free body diagram is great. Of course, a system schema may help clear things up as well. This question is asking for the tension in each of the vines. And so it's possible, kind of like the feet, find the tension in overall, and then maybe divide by 2. Because they're at the same angle, chances are you'll be able to simply divide by 2. And then there's an add-on question. What would happen to the tensions if the upper ends of the vine were farther apart? So what if this angle changes? What do those vines have to do? Do they exert less force, make it a little easier to support the gorilla, or would it take more force? Okay, if you've already worked this out, keep the video going. The solution will come up. I think I hand wrote this one in. Otherwise, if you haven't, give it a shot. Set it up, try it, and come on back and go about 9.5 minutes into the video, and then you'll be able to go see the solution. Well, here we go. Okay, so again, this is the whole thing in total. Here's my force diagram. And with this force diagram, maybe not quite to scale, maybe to scale. Here's the second vine, here's the first vine. I arbitrarily assign them, 1 and 2. From the vertical, here's the 30 degrees. From the vertical, here's the 30 degrees. So that's how I know how to set up the trig. My force of gravity is straight down. Therefore, these two forces in their upwards direction, so this leg of the triangle, which would be the adjacent side for both of these vines, given that this is a hypotenuse and that's a hypotenuse. So the up force, the restorative force, the normal force, if you will, but in this case it's really the tension force because we're dealing with a vine or a rope or a chain or a string. We call it a tension force. That this force each added together will be exactly the same as the down force because the gorilla is static. It's just kind of hanging there. Okay, so what do I know? Well, I know the mass of the gorilla, I know the angle, and I know gravity. What are the questions? What's the force of tension in the first vine, the second vine? And I know these two tensions are equal because the angle is the same. Here is just looking at the force of tension 1. Here's the vertical tension. Here's the horizontal tension. And what I'm looking for is the hypotenuse here. Okay. So what can I do? Well, I can come down here and say the force of gravity is equal to mass gravity, so I can solve for this value here. And I know that the vertical 1 plus the vertical 2 of my vines must equal the opposite of gravity. And I know that each of these two vines are the same, so their verticals will be the same. So I can then solve using a cosine function. Okay, coming over here, I believe I've got a plug and chug ready to go. So the force of gravity, here's the mass of the gorilla, here's gravity, and there's that force pulling down. I know that the sum of the two vertical components of the vines must equal that value, positive, of course, and that the sum of both of these equaling that must be that the force of one vine is simply half of that. So I took this value in its positive sense, and I divided it by 2. So that's the force up. So if I want to then know the hypotenuse, because remember what I solved for was a component, not the hypotenuse, that I would then take this and I would send it through the cosine function in order to figure out the hypotenuse, the actual tension on the vine. Not what it's doing up, not what it's doing out, but what the vine is actually doing, what the vine is experiencing. So I sent it through a cosine function, ended up being 1755 newtons, and to sig figs it's 1760. Each vine then has exactly 1760 newtons, appropriate sig figs, for that. Okay, in the paraphrase, each vine experiences 1,760 newtons of tension as the gorilla hangs from them when the vines are at 30 degrees from the vertical. If the angle increases, then the vine tension will increase, i.e. in S, I believe, from the Latin. At 45 degrees, the force of tension goes up to 2150. So it increases from 1760 at 30 to at 45 degrees, 2150. Until the tension, the force of the tension in the vine maximum is reached, when the vines would be completely horizontal, which would almost be like a gymnast in the Olympics when they can take something completely horizontal and still hold themselves up, which is, I think, actually impossible. But along those lines, they come close. So there's number 4. And onwards to the last one, number 5 for problem set B. Problem set B, number 5, is about Zorba, the giant mastiff, and this is a challenge question. There's a lot of trig involved in this one. The massive Zorba, born in London, England in 1989, so he must be passed away, unfortunately, by now. 155 kilograms. Again, 2.2 pounds per kilogram tells you that this is a 300 and some odd pound dog. 2 average adult male mastiffs. So he's twice as big as the other mastiffs. And you can read the rest of the question. He's placed in a harness. There are two cables. They're right angles to each other. If the tension in one is twice as large as the tension in the other, what are the magnitudes of the two tensions? So that's the interesting twist. Unlike the gorilla, which had equal tensions, now we have different tensions in the cable that you have to accommodate. However, the math is not all that incredibly hard because one cable is simply twice the other. That would be like if the gorilla had force of tension 1 was twice that of tension 2. So if you solve one, then you either double or half it to find the other. So it's not that big of a stretch, but it is a little bit more challenging. What are the magnitudes of the two tensions? Assume the mass of the cables in the harness to be negligible, so we don't have to worry about any of that. All we have to worry about is Zorba's mass at 155. Of course, always draw a force diagram and a system schema if you think it helps. Now this one I did not handwrite out at the time I was preparing this. I didn't realize it, and so I just grabbed really quickly the book solution. So it's not set up with GRASP, but it is the book solution. You can follow along. Here again, if you haven't solved this, I'd say try it. You know, you can do the best you can. And then come on back and take a look at what the solution is. So here's the solution. Ah, that was a trick. Here is the solution. It is coming now. Okay, here we go with the solution for the challenge question for Zorba. I lost my place, and so I'm re-recording, and I'm hoping that it picked up at the appropriate point. And so here we go. Okay, so this is not, of course, set up through GRASP, but here's the givens, and I am, here is the requested right there. So what do we know? Well, this is coming from a force diagram, which is not drawn here, and you would see that the cables themselves are at 90-degree angles from each other. One would be much steeper than the other, and so therefore it's going to bear more force. The one that is at a gentler angle, I guess, that is not so vertical, will have less force. So what I know is the force of tension of cable 1 is twice that of the force of tension of cable 2. So that's an important distinction to be made. There's the mass of the Zorba Mastiff, gravity, and of course my angles. Angle 1, which is 45 from the other, so that's 90 minus angle 2, which will give me angle 1. Okay, well, I know all the net forces equal up to 0, so the net forces in the x direction, which is the horizontal direction, will equal 0. Now, all this will come from your force diagram, so you can see the oriented triangle of the situation, so you can derive the trigonometry from it. But here I have the force of tension of cable 1 multiplied by the cosine of its angle, less the force of tension 2 times the cosine of its angle will equal 0. Here is the net forces in the y direction also equaling 0 because the mastiff is not going up or down either. And so that would be, again, a sine function now based on how the triangles are oriented for the force of tension of cable 1 and cable 2. So there's just the sine functions. Less, of course, mass gravity, because all of that together would equal 0. So these are the two forces up. That's the force down. All of it cancels, equaling 0. Okay, coming back to the force of tension of cable 1. This would be a product, again, equaling 0. Cosine of angle 1 minus half of cosine of angle 2 as we combine these two terms together. All of this will equal 0. Okay, let's deal with the angles. Twice the cosine, okay, actually what I should say is where I lost my place last time. Condensing these two, simplifying, pulling it out, you have 2 times the cosine of angle 1, which is going to equal the cosine of angle 2. All of this will equal the cosine of 90 minus angle 1, which is a reference back to here. And if cosine of angle 2 equals the cosine of this, that will equal the sine of angle 1. So, sine over cosine is tangent. So 2 equals the tangent of angle 1. So basically just simplifying this phrase, which comes from here, allows us to get to this point. And so, solving for the angle at this point, angle equals the inverse tangent, or arctangent if that's what you call it, of 2. Well, the inverse tangent of 2 is 63 if your calculator is set in degrees mode. So now we have an angle. The angle, the force of tension, vine 1, or cable 1, I guess it's a cable this time, is 63 degrees. Well, angle 2 of the other cable is going to be 27 degrees. So interesting how we could start with very little information and end up with being able to use the trig to figure out the angles. So 63 and 27 respectively. Okay, well, force of tension to cable 1, sine the angle, plus force of tension of cable 1 divided by 2. Remember, it's twice that of number 2. Sine of angle 2 equals mass gravity. This is simply restating our net forces in the y direction, but we have information now, and so we're pulling this down here. Okay, well, let's rearrange and actually solve for the force of tension of cable 1. So mass gravity divided by everything else. We have angles now that we can put in there. And so if we do that, here is the plug and chug. So that would be most of all of this is really the analysis phase, although there's a little bit of math here. And then here's the solution phase. So mass, gravity, sine of angle 1, sine of angle 2 divided by 2 because of that, the twice, the factor of 2. Solving for all of this, it turns out that the cable 1 has 1,360. That's a misprint, but 1,360 newtons, and then half of that would be the force of tension of cable 2 at 680 newtons. So, a little bit of trig here, and I should have handwritten this out. Of course, now I'm really thinking about it, just in the fact that that force diagram would be really nice to see, just so you can start to ferret out this information. You still have to be able to condense down. You have to be able to pull it together here, simplify. You don't have to resort to the tangent here. You could actually go through the other math, but this actually works much better. To be able to resolve the sine over the cosine in simplification to get to tangent. Anyway, there you go. That's number 5, second attempt at it. And so I hopefully, as long as you didn't hear the first one, this had to be clear, right? Okay, well, thanks, and I will attempt to make sure that I do this for problem set C, D, and E, which will wrap up the chapter for Chapter 4. Thank you.